Hello students, I am back to you once again with a new topic for discussion. The new topic is missing data. You might recall that in my previous two modules I discussed a little bit about the possibility of missing data in various situations. Now this missing data can occur in every respect. It might be due to the mistake done by the investigator in recording the data, or it might be that some of the households or individuals are reluctant in giving the response. So by way of other, missingness occurs in many situations, and just replacing it by randomness by some value is not really serve the purpose, will not serve the purpose, and so one should be careful about scientifically using or imputing the data in the missing position, so that valid inference and strong inference can be made. So we start our discussion on missing data, its uses and its analysis. What is certain in life? Death and taxes. What is certain in study? Missing data and measurement errors. You know that missing data can be due to preventable errors, mistakes, or lack of foresight by the investigator, due to problems outside the control of the investigator, deliberate, intended, or planned by the researcher to reduce cost or respondent burden, due to differential applicability of some items to subsets of respondents, and various other reasons. When do you see missing data? What are the types of missing data? What are the traditional approaches? I will discuss that. Deletion and substitution, these are the two traditional approaches. And the modern approaches, the maximum likelihood and Bayes, and some software, if time permits, in this connection will be discussed. As regards its application, it is used in medical studies, non-response in surveys or censuses, dropouts in clinical trials, census data, and everywhere where data is not recorded properly. And what is the result of that? Loss of information, loss of power, bias in results due to differences in missing and observed data can be seen. The complicated analysis with standard software has to be done. So what's wrong with completed analysis? It is inefficient, it is problematic in regression when covariate values are missing and models with several sets of explanatory variables need to be compared. Either we keep changing the size of the data, or we add or remove explanatory variables with missing observations, or we use subset of the data with no missing values. You see that what happens is that when you go on reducing the data set because of the missing observations, ultimately this subset may reduce to very small data set, and as a result the information may be less and the inference will be much weaker. When the missing observations are not a completely random selection of the data, a completed analysis will give bias estimate and invalid inferences. One approach is simple mean imputation. So essentially the idea is that whenever there are missing observations, it is better to impute scientifically some value so that the whole data set becomes a complete data set and you can make valid inference out of that. So this is the first approach here, is that we consider simple mean imputation. So wherever we find any missing observation, we replace this by the arithmetic average of the observed data for that variable. Why not? What is the problem there? This approach is clearly inappropriate for categorical variables. You know that when you take the average of categorical variables, it becomes a decimal, it might become a decimal value, and then naturally it is not appropriate to fit in the missing position. It does not lead to proper estimates of measures of association or regression coefficients. Rather, associations tend to be diluted. In addition, variance will be wrongly estimated if the imputed values are treated as real. Thus, inference will be wrong too. Now, another possible approach is the regression mean imputation. I just try to explain this. Essentially, whenever you see some observation is missing, take that variable as your predictor variable, and you predict that variable by using another variable for which the complete set of observations are available. So, let us look at this table. See, you have a data set where you have two columns 1 and 2. For variable 1, all the 10 observations are available. On the other hand, variable 2, last observation is missing. No matter which one is outcome or response, which one is your explanatory character, you make a regression with y as your variable 1 and x as your variable 2, and you go for the regression analysis. You see that, like in this regression problem, I use V2 as the variable y and V1 as the variable x. So, variable 1 for which all the observations are available, I use this to predict V2 by using 9 observations that I showed in the table. So, I am going to make the regression, and based on the regression I find the estimate for alpha and beta, and after estimation we predict V2, like we got that V2 is the estimated value of alpha is 6.56, whereas the estimated value of beta is minus 0.366. So, this is the regression equation, or based on that, for available value of V1 I can predict the value of V2. So, in this particular example we see that V2 comes out to be 5.24. So, in this table, in the missing position, we substitute 5.24 to get a complete data set. We then go for analysis and draw our inference. All right. Then there are still some limitations of regression mean imputation. Why and why not? Regression mean imputation can generate unbiased estimates of means, associations and regression coefficients in a much wider range of settings than simple mean imputation. However, one important problem remains: the variability, which is very important actually. The variability of the imputations is too small. So, the estimated precision of regression coefficients will be wrong and inferences will be misleading. Now, we go for some notation that is used to study the various missing pattern and the modeling and others. So, suppose we have the whole data set y, and for which we have y naught the data available and ym the data missing. So, I accumulate all the missing observations under ym and all the available observations under y naught. All right. Then we introduce some missing value indicator. You see that just previously y does not mean that it should be the response, it may be any explanatory variable for which observations are missing too. So, let us go for a missing value indicator which is r if y observed and r equals to 0 if y missing. The key question then comes up is that under what circumstances, if any, do the analysis we would perform if the data set were fully observed lead to valid answers. What I mean here is that valid answers is actually the estimated value should be such that based on the missing data, when we estimate the missing values and substitute that, then it might be the estimate of the parameters and the test procedure will be as consistent as possible, so that more or less correct inferences can be made with the missing data. So, this actually depends on the missing value mechanism, and that is the probability that a set of values are missing. A set of values are missing given the observed and the missing values. We use the notation probability R given y naught and y m. We use that subsequently for modeling, but let us go to some examples of missing value. Like the chance of non-response to questions about income usually depend on the person's income. If the person has higher income, he or she may hide his or her income interval or income level. Okay? And someone may not be at home at the time of interview because he or she is outside for work. The chance of a subject leaving a clinical trial may depend on their response to treatment, and a subject may be removed from a trial if their condition is insufficiently controlled. It might be the situation that the person can be removed from the trial, like suppose a person is having the cancer, stomach cancer, and at the final stage it is not very advisable to come on frequently and go for checking and other things. So, this time he or she may be advised to take rest, stay back at home. Okay, so, this is a one situation where the missingness occurs. So, there are three types of missing data. One is MCAR, one is MAR, and the last one is MNAR. What is MCAR? It is missing completely at random. That means, this missing data probability that I mentioned earlier, that this probability that the observation is missing does not depend on the value or on value of other variables. It does not matter if it is associated with other missingness too. Missing completely at random is the simplest type of missingness pattern. So, what I want to say here is that probability R, the observation is missing or not, depending on y naught and y m, does not depend on the observed or unobserved measurement. All right. So, this is missing completely at random. So, missing completely at random is the very simplest, as I said, and it is helpful to in getting the consistent estimate of the parameters. Anyway, so come to the next one, which is MAR, which is missing at random, and here in this case missingness depends on the variable, except that it can depend on other variables too. This is not great, but we can deal with it. Missing at random, what we wanted to mean last time in the last slide is that probability R given y naught y m is probability R given y naught. That means, it does not depend on the missing observations. So, an observation will be missing, will depend only on the observed value, the values of the variable which are observed only depend on that, but not on the missingness. And finally, the other one is MNAR, missing not at random, not MCAR, which is not MCAR, not MAR. So, pretty bad. Model missingness is also another issue for consideration, but missing not at random situation is quite complicated. We say that the data are missing at random when neither MCAR nor MAR hold. Okay. In that case, the likelihood setting the missingness mechanism is termed as non-ignorable. The situation is a typical situation. Mathematically, we can show that it cannot ignore the missingness probability part from the likelihood, but in the other two situations it was possible. I explain it more details. What this means is, even accounting for all the available observed information, the reason for observations being missing still depends on the unseen observations themselves. To obtain valid inference, a joint model of both y and r is required. That is why it is non-ignorable. Otherwise, in MAR or MCAR case, the valid inference can be drawn based on the likelihood of y only, but not r. The traditional approaches are like deletion, as I said earlier, the deletion and pairwise deletion. So, these are very simpler type old approach, but not stochastic approaches. But these days people are using some imputation techniques, although we consider initially the single imputation, but single imputation is not really very strong. Rather, modern technique is the multiple imputation technique, where you are able to get almost the same inference had there been the complete data set available. So, single imputation technique includes hot deck, then cold deck, then mean substitution, regression substitution, stochastic regression substitution, etc. And in the modern method, we consider maximum likelihood, like the EM algorithm, estimate parameters, where EM is expectation maximization algorithm, where the parameters are estimated based on the predicted values of the missing observations given the data, and then these predicted values are substituted to ultimately find efficient estimate that converges to the maximum likelihood estimate. One can see the following website for the detail of EM algorithm. The principled methods, the great range of ways in which these can be done leads to the plethora of approaches to missing values. Here are some broad classes of approach: wholly model based methods, simple stochastic imputation, multiple stochastic imputation, weighted methods. There is another point, is the random imputation, where predict missing values, then add error component drawn randomly from residual distribution of the variable, repeat several times to improve error estimates. We considered the most modern technique, multiple imputation, for analyzing the missing data. Now, it is basically on the basis of on the basis of the idea of Bayesian arguments. So, what we do is that we consider a parametric model for data, and it may include ignorable missing data or non-ignorable missing data in the model. So, then we look for the prior for the parameters appearing in the model. As I said, that this is based on Bayesian arguments. So, prior for parameters in the model needs to be taken into account, and then we simulate M independent draws from the distribution of y missing given y observed. That means, based on the observed value, we generate M blocks of predicted values of y missing, and then we calculate these values, or rather the missing values, explicitly through MCMC technique, Monte Carlo Markov chain technique. Let us discuss this Monte Carlo Markov chain technique. In fact, in the multiple imputation procedure, while applying the Monte Carlo Markov chain technique, we first of all generate unknown parameters from the observed posterior distribution. I mean, from the posterior distribution given the observed data, I should say that way. Then we simulate a random set of missing values from the conditional predicted distribution. And so what is happening that first in the Monte Carlo Markov chain technique, initially we generate observations on unknown parameters given the data, and then generate observations on the missing values given the data. We repeat this, obtaining new parameter estimates from complete data set until it stabilizes. So, this Monte Carlo Markov chain technique, which has been introduced by Tanner and Ohm in 97, gives us the all through the given the data, the joint posterior distribution of the predictive observations and the parameters of interest in the model. So, based on the predictive observations, we substitute these predictive observations rather in the missing positions to get ultimately the whole or complete set of data, and then we go for the complete data set analysis. This is how the missing multiple imputation procedure is carried out. We calculate parameter from, because I said that there are m sets in multiple imputations, there are blocks of generations for every missing observations and the parameters. So, suppose there are m data sets generated by this way, we calculate the estimate of the parameter and just take the from each data set, and then just take the average of m such values of q, and then also compute based on the m data sets the variance of q, and it can be shown that as the data set number of data sets get large, then we can get the consistent estimate of the parameter q from the data. So, the variance of q can be computed as t, which is 1 plus 1 over m b. B is the between sum of square given below, and u is the mean within imputation variance, that is also considered. So, as m tends to infinity, this t tends to actually the true variance of the estimate q. Okay? So, this is how the multiple imputation has to be done, and the parameter estimate has to be done, and accordingly the multiple imputation has to be done to fill in the missing data.